Hi, my name is Rebecca Ramirez, and this is my pencast, and this is for homework problem 1, and my name is Rebecca Ramirez. I don't know if that's part of the rubric. I'll double check in a minute. But you have my name. And then this is my pencast. Okay, so step 1 would be read the problem. Two 5.0 gram point charges on a 1.0 meter long thread repel each other after being charged to positive 100 nanocoulombs. What is the angle theta? You can assume theta is a small angle. Okay, so from there we know we're going to use a small angle approximation. So I'm going to write that down because, that's simple points you would get wrong in an exam if you didn't read carefully. And then from there we have two 5.0 gram point charges. So our mass is equal to 5 grams. Grams is not the proper SI unit, so we know we're going to convert to kilograms in a minute. Or not in a minute, but later on in the problem. And then we have our length, which is equal to 1 meter. And then we have our charge, which is Q1. So Q1 is equal to Q2 because both have the same charge and have the same mass. So it equals mass 1, which is equal to mass 2. But we can just call it M, and Q, which is equal to plus 100 nanocoulombs. Again, we're going to have to convert this into proper SI units, so regular coulombs. But we'll do that in a bit because right now we're just going to focus on symbols because numbers are a little bit confusing if we start with very large numbers from the beginning. And then our unknowns are theta, and then our second unknown is this length, and this length is D. D is also known as R if you're using the point charge equation, but we're just going to call it as D because it's the distance between the 2 point charges. You can call it anything else, but that's what I'm going to call it. And then we're going to do our free body diagrams. Is this oriented properly? I hope so. Okay, so you're going to draw your X and Y. Hope this is long enough. X and Y. Okay, and then from there you can use this diagram to orient yourself on this diagram. And you want to make sure you do your X and Y because that kind of helps you out when you know what's negative, what's positive, when you have your total forces or total vectors aligning up later on. So this is going to be our first vector, and this is going to be the tension on the string. So it's T. And then we're going to have, so this point charge is a mass, so we're going to make sure to account for that, and that's force of gravity, which equals mass times gravity. And then we have our, so two like charges repel, so we have Q2 putting force on Q1, so that's going to be force of 2 on 1. You can call this anything you like, but I think that's the easiest way to put it because that's what the textbook uses. And then from there we're going to do our F net equation. And that's going to be, can you see that? I think you can. Force net, which is equal to our 3 vectors from the free body diagram. So that's going to be tension plus force of gravity plus F2 on 1, which is equal to 0. And then we're going to do our X and Y orientation of this because we can't just have it one force. This is looking at it from a 2D perspective. Okay, and then this is our theta, and then this is our 1.0 meter, and then this is the diagram looked at it from a triangle. We can use this triangle to orient ourselves with the X and the Y. So we have our F net and the X, and then we have our tension. Okay, so here we know that this is moving in the X direction, so we know tension is going to be a part of that. Then we're going to put tension of X. And then we're going to have our, what else moves? Okay, so this is 0 for the X direction. So we know we're not going to use force of gravity in this equation. But if you did, later on, you just put a 0, because it's 0 of, so it's 0 of force of gravity, 0 comma force of gravity, our usual math notation of it. So then we have, this goes off in the negative Y direction. But right now we're just going to have it as force of 2 on 1. And you can put it as X, but you could also just not put it as X because, that's our total. It only goes in the negative X. It doesn't go up in the Y direction, so it's kind of similar to this. But you don't have to put the X here, but I'm going to put the X there. And then F net y, and then we have our t of y, because it does go off in the y direction, and then this goes off in the y direction. And for the same reason, we don't put this in the y direction because it doesn't go up, it just goes out in the x direction. So force of gravity, go to 0. You can put it as y, but you don't have to. Okay, so then from there, we're going to use our triangle to orient ourselves with our tension, because we don't have what tension is, but we can use this triangle to identify what it is. So we have x, and then that's t, and then our t is, okay, so it's opposite over hypotenuse, so that's going to be sine of theta. And then if you remember here, this, okay, we're doing x, so this goes off in the negative direction, so we're going to subtract force of 2 on 1, which is equal to 0. Okay, and then we have our y, which goes off in, that's this side, it's our adjacent. So we're going to do adjacent over hypotenuse to get our y, because we can't use this side because we don't know it, so we'd have to do this in our known side. So it would be t cos theta, because cos is adjacent over hypotenuse, minus force of gravity, because it goes in the negative direction, our tension goes in the positive direction. So it's 0, and then negative, and then it's negative 0. Okay. So then from there, so that's all given by our x and y, so it's really important that we put that down. We can look at our t, because this, we actually have all the knowns for this. We don't, well, it's up for theta, but we don't have all the knowns for our x equation, so we're going to start off with that one. And we're going to do t sine of theta is equal to force of 2 on 1. We're just moving this to the side, and we're going to make it positive. So our t sine of theta is equal to, so this would be the point charge equation, which is k times q1 times q2 divided by r squared. So our r is going to be d divided by 2 is equal to r. That's because the total d is the whole distance, but it's a right triangle, so we're only doing half of that distance. So that's going to be what r is. So this is going to be q, oh, we're going to make q1 and q2 just q squared because they have the same value. I think I mentioned that here. And then we have d squared. And then from there, t sine theta. Oh, and then we're just going to make this equation all in terms of k, or of our knowns. So we have d, which is unknown, so we're going to identify what d is. K times q squared divided by d divided by 2 squared. So then we're going to do sine theta. We know this, and it's a constant, so we can just take that out. Well, we don't know t yet, but like, we know enough about t right now to just eliminate it, because it's a constant. And then we're going to get d divided by 2. Oh, these are constants. Remove those two. You can just get rid of that because that's also a constant. Divided by L. So D is equal to 2L sine theta. And then we can use this. Oop. Have you not been seeing this the whole time? Let me see. Okay, I think you have been seeing this. Okay, let me show you the total of what I've written. I'm just going to have you catch up on that. And then we're going to go back to this. Okay, let me try to move this. There. Does that work? Can't really see the whole paper. Oh, that's annoying. I've got a projector. Okay, I'm just gonna hold it. I hope this isn't annoying. Okay. Okay, so we have dl sine of theta, and then from there we're gonna put this back into our sine of theta equation, which is here. So then we're gonna have t sine of theta, which is equal to k times q squared divided by d, which is 2 d squared. Sorry, I have to take a pause and just jump. It's kind of harder when you're holding your whole thing. Let's see. 2, it's going to be 4. Okay, 2L sine of theta, which is squared. And then from there, yeah, so then from there, we're going to have, sorry, I'm just taking it back because it's kind of harder to like look at what I'm doing and look at the camera because I want to make sure you guys are looking. Okay, so we have this equation, so now we can use t cos of theta, which is equal to m times g. So from there we can do, I'm going to move this over here, that's okay. So this is divided k times q squared divided by 4L sine squared theta times m of g. So this can become, eliminate these two, and that's going to be tan of theta equals k times q squared over 4L sine squared theta times mg. And then from there, we're going to move all our sines and our tangents to one side because it has the theta as well. So it's like x moving on to the other side. So it's going to go sine squared theta tan theta, which is equal to k times q squared divided by 4L sine, or nope, m times g. Does that look like an m? Okay. And then from there, we can just get a number for those because we do know all the knowns for the right side, so that's going to be 9.00 times 10 to the 9th newtons meters squared divided by coulombs squared. Double check my units, yep. And then, dang it, I don't have enough room. Times q squared, which is 100 newtons. Actually, maybe I might, no, it's fine. Newtons coulombs squared, and then this is going to go like this, divided by, this is also like divided by the same thing. Hope that's not confusing, but we're dividing, okay, this whole top part is our k times q squared. And then we have 4 bracket times L, and our L is 1 meter squared times grams, and we have 5 grams. So then we have to also, remember that we don't have the proper SI units, so that's going to be 100, actually that's going to be confusing because it's on the top, so we're going to do 1 coulomb is equal to 10 to the 9th nanocoulombs times 1 kilograms is equal to 1,000 grams, and then our total turns out to be 4.59 times 10 to the minus 4. And then from there, we can use the small angle our small angle approximation, and that basically says that theta is really small, so sine theta is equal to tan theta. So then theta turns out to be sine theta. And then this is going to be sine to the 3rd theta, which is equal to 4.59 times 10 to the minus 4. And then from there, we can take cube root of that. So that's going to be, sorry, I have the numbers written down on my left. So theta is equal to sine, and then we take the inverse sine after that, 0.07714. Okay, and you can double check on your answer, which is 4.4. 4.4 is our angle for the problem. Oh my god, sorry. I'm having a really bad brain fart. Because we know that it's a really tiny angle, and then I think I mentioned, okay, focus, that it's a small angle, and then we're going to use a small angle approximation, which we did here. And then our small angle approximation also states that sine theta is approximately equal to tan theta. And then that's my pen cast, and I hope that was helpful. I'm going to have it there for a moment so you can just pause the screen if you need to double check your answer.